Thanks for coming out. I think this is the last session today, right? Okay, so great. Thanks for joining us for droidCon, and I hope you guys have had a good time so far. So we're going to talk about 3D scene rendering, and it's good that you guys are here because this is kind of like the forefront of like where computing is going. If you've kind of paid attention, we're kind of moving towards an era where we're going to be doing more in VR and then eventually in AR. I think everyone agrees that AR is pretty has a pretty good chance of being the next big computing platform. So we're going to learn about 3D rendering, and we're going to learn about it at a little bit deeper of a level than if you use some high-level APIs like Sceneform, which is the API that Romain Guy worked on, which kind of just lets you load in a 3D file and then render it. So I'm going to talk a little bit more at the nitty-gritty level, and then I'll also give you guys some information about the 3D post feature on Facebook that uses the glTF format, which I have a t-shirt of. So you know I'm serious. I happen to be the face of VR, no big deal. Yeah, that's me. Just want to throw that out there. So yeah, we're going to start by talking about 3D posts on Facebook, and then we're going to go into the details of the glTF format, which we like to call the JPEG of 3D. And then I'm going to talk to you a little bit about some improvements that we're making in 3D posts. So 3D posts kind of started like this. We launched it giving the ability to interact with 3D objects, which are rendered directly in real time into your Facebook for Android or Facebook on the web or on iOS as well. So this was a partner, Lego, that launched with this brand video of them, or brand 3D model of their parrot. Pretty cool. But actually, we started trying to support this other use case of we have these VR creation tools, which allow you to create 3D models, sculpt 3D models in VR. So this is Oculus Medium, and we wanted to support sharing from VR directly to newsfeed so that we can extend the reach of creators. So this is an example of what that looks like. So you'd have someone sculpting out art, 3D models directly in VR and then sharing it to Facebook with a click of a button, and that will just create a glTF file, which they can then share in newsfeed. So that was first-party integration, but earlier this year, I think in February, we supported dragging and dropping a binary glTF file, .glb extension, directly into Composer, essentially making 3D a first-class citizen on Facebook akin to photos and videos. So just as easily as you can drag and drop a photo or video into Composer, you can drag and drop a 3D file in glTF format, and then change the background, play around with the the initial view of the object, and then there you go. You can interact with it in newsfeed. That's great. So what this allows us to do is we empower these artists to be able to share their 3D art assets from games. So for example, this is an asset from the game Brass Tactics. And you can see it rendered in Facebook for Android there. And then a recent feature that we launched was 3D photos. So 3D photos kind of just sits on top of the 3D post architecture. Behind the scenes, this is using glTF 3D meshes. Some of you may have seen this already. I think we launched this maybe a few weeks ago. So what you can see is basically it seems like a static image, but then you can tilt around and it gives a little parallax effect. The way this works is that we have the RGB color value and then the depth value that comes out of a camera, like the iPhone camera that has the two separate cameras to get the depth disparity. And then we can generate a depth map from that, or we can use the depth map from that to generate a mesh. So basically we'll have our background mesh and then our foreground mesh, and then we can apply the parallax by just moving the scene around. So this is pretty cool. So let's get into the actual format itself, glTF, and why we call it the JPEG of 3D. So back in the day, John Carmack, who's the CTO of Oculus, called for the creation of the JPEG of 3D to build the metaverse. What he was asking for is we didn't really have a 3D transmission format. So we had formats that were used as interchange within different authoring pipelines locally on the artist's machine, but we didn't have anything for delivery over the web in an efficient way. So if we look at the history of transmission formats on the web, for audio, we always kind of had a big player that pushed a format forward. So for audio, we had Napster that pushed MP3 forward. For video, we had YouTube that popularized H.264 video encoding. And then, of course, for JPEG, Facebook pushed that forward heavily. And then we're hoping that for 3D, that our adoption of glTF will help push the ecosystem forward and get more players to adopt the glTF 3D format. So why do we need a new 3D format? So if you look at some of the formats that exist already, FBX is a very popular format created by Autodesk. A lot of artists use FBX. But it happens to be non-standard, so it's not easy to validate, which leads to inconsistent implementations and some ambiguity. And it also doesn't support extensibility, so we can't just add things that we need when they aren't there. And it doesn't support newer features that we want in a 3D scene format, like physically based rendering, which I'm going to talk about a little bit later. OBJ was, also very popular, but it's like a plain text format. It only describes objects, but we would need to describe full scenes with, animation and lighting and transforms and so on and so forth. DAE was actually, or Collada, was a format that the Kronos group created to try to solve these problems, but they created it as an interchange format. So they used XML. It wasn't that efficient to load, and it ended up being bigger files. So it didn't really solve the problem of being an efficient transmission format. So the properties of glTF are that it's compact to transmit. So it has a JSON description of the scene graph, and then it has a big binary blob, essentially, where it keeps all the mesh data and all the animation data and anything else you need to render the textures and so on and so forth. It's fast to load because we can just take that binary data and do a data copy and then upload it to the GPU instead of having to parse all the data and then create buffers in memory and then upload those buffers to the GPU. It describes full scenes, so we have complex lighting, we have the ability to do animations and joint-based animations and blend shapes and natural lighting techniques like physically based rendering. It's also runtime neutral. So actually the first version of glTF, glTF 1.0, wasn't runtime neutral. It was kind of designed for OpenGL, WebGL, and OpenGL ES. But the 2.0 version was designed to be platform agnostic. So you could render it with DirectX, you can render it with OpenGL, you can render it with Vulkan or Metal. It really describes things at a high level, and it's up to the renderer to interpret that. And it's very extensible, so they encourage the creation of extensions for vendors. So, a popular example of this is, Microsoft has made a bunch of extensions for levels of detail, and Google has also made a very popular extension for mesh compression that I'm going to talk about a little bit later. So now we have like a pretty big ecosystem where we have the creation tools like Blender and SketchUp and Substance Painter and Oculus Medium, of course, that allow exporting glTF files. And we also have converters. So we open sourced a converter from FBX to glTF on GitHub, which allows people to work within their existing pipeline, but then still be able to work with glTF. And then we have the content sites like Sketchfab and Google Poly that provide glTF assets. And then we have the app and engine integration with apps like or engines like Unreal and Unity supporting glTF through plugins. And of course, React VR supports glTF. So things are looking pretty good right now in terms of industry adoption. So what's in the actual glTF? So to start, there's the scene hierarchy or the scene graph. There's the geometry data. There is data for the textures, which are just images that map to the mesh that is representing the actual physical geometry. And then there's animation data and skin data, which essentially is used for when you have joint-based animations. And then all that gets combined together and interpreted by the client, and that will be used to render the final scene. So the glTF file itself, when you have the binary glTF, it'll just pack all this stuff together in one binary file. But it's going to be composed of the JSON part, and then it's going to have the binary part that's going to have the vertex data as well as the index data, and I'll talk about what that means later, as well as the animation stuff and skins and the texture data. The JSON structure has a bunch of high-level array objects, which are the entities that are used to describe what the scene graph is. So at the top level, you'll have the scene, and then the scene can have multiple nodes, and each node could also have multiple node children's. And then each node will have a mesh. And then the mesh is going to get down into the details of the actual triangular mesh that represents the object itself. And you can also have the camera, which describes how we're looking at the scene, which is important. And then, of course, the material information is just how we're going to provide the texture or the look of the actual geometry. A very simple example of this is, let's say we have this scene that we're going to have this car, and the car is going to animate, it's going to drive forward, and the wheels are going to rotate. So this would look like what you see above here, where you'd have the root of your scene, which would have a car and a camera as children, and the car itself, let's say we can compose it into the front wheels and the rear wheels. Now, each node can have its own transform. So it could have a transform applied at one level, and it will be applied to all the children of that node. So for example, if the car is moving forward, the wheels will also move forward because they're children of the car. But at the same time, you also might want to have independent transformations or rotation, translation, scale applied to the wheels. So for example, you want the wheels to rotate while the car is moving forward. So those wheels will have their own rotation matrices applied to them. So that's all specified within the JSON. You'll see that there's a bit of indirection here. So the way we describe the children of a specific node is we give indices into that JSON array to where to find that node. So the node array is just one big flat array, so that there's no multiple levels that you have to jump through to find the children. This makes it super easy to parse, especially on the web. So all you have to do is just look at the reference to the index and then just look it up in that one JSON array. So this is all by design. It adds a little bit of indirection, but it makes it more efficient and faster to parse this. So now we're going to look at the Hello World example of a glTF file. So this is a glTF file that just renders a single triangle. A triangle is the primitive for graphics rendering in most APIs. Sometimes it's a quad, but on OpenGLES, it's a triangle. So this is what the entire glTF file will look like over the next 3 slides. So you'll see that we have a scene with a single node, and that node has a single mesh 0. And then at mesh 0, it's going to have information about where to get the vertex data and the index data. So that's in that primitive section. And where you see position, that's a keyword that refers to the vertex data. And the one that you see there is just the index into the accessor array that I'm going to show you in a second. So what does this look like in the buffer? So what we're going to have is we're going to have the information to describe that triangle, which is going to be composed of 3 vertices, vertex 0, vertex 1, and vertex 2. So a very important thing in when we do mesh rendering is we want to make sure that we don't have any redundant vertices. So the way that we do that is we list out every single vertex, and we pack that into the data. And then we have another index buffer that references the vertices there. That way, let's say we're trying to draw a square here instead of a triangle. Let's say you flipped a triangle and then put it on top of this one. You'd be sharing vertex 0 and vertex 2. Now, we don't want to duplicate the data for those vertices, because if you had a really complex mesh, it'd be super inefficient. So what we do is we just use the index buffer to describe the entire geometry. So in this case, we're going to allocate 6 bytes, and we're using 2 bytes for shorts. So there's going to be 3 entries, and it's just going to say, look at vertex 0, look at vertex index 1, look at vertex index 2. So that's the first 6 bytes. And then the next 36 bytes are just going to describe the actual vertex positions in 3D space. So it's going to be a vector of 3 floats. So in total, it's going to be 36 bytes. And those 2 elements, the index buffer and the vertex buffer, basically tell us exactly how to render or how to describe our triangle. And a more complicated example with a more complicated mesh, in the end, just comes down to this kind of thing. So our buffer data, in this case, because we have very trivial data, it's just a triangle, we can specify it with a data URI and then just give it the byte length. But normally you would have your mesh data appended to the end of your GLB file. So that way you would just provide an offset into the same file to where to get that data. Now, your buffer views are an abstraction that allows you to look at the same buffer. Because remember, I said that we're going to want to be efficient with the way we load our data. So we want to take one buffer and then just look at it to find the things that we need. So we might have a stride applied to that, or we might look at it from a specific offset to find the data. So in our case, we're looking at something like this. So we know that we're going to have a byte offset 0 to 7 and then 7 to 43 to describe where we're going to find our index data and then where we're going to find our vertex data. So that's essentially what the buffer view provides there. So the accessor is the thing that hooked up to back here. So remember I said the position value 1, that's referring to accessor 1. And then where it says indices, that's referring to the index data that we can find in accessor 0. So that refers here, and it just gives another reference to the buffer view that we just saw. And it's going to give you information about the component type. So in this case, it's going to be either float or short, depending on the index buffer or the vertex buffer. And then, of course, it gives you the byte offset for where to find it, how many elements are in there, and if it's a vector or just a scalar. And then the min and max is just like the bounding region. And then finally, we provide the asset version because there's different versions of glTF, so we want to make sure that the client knows how to parse it properly. So I've actually provided some sample code on FBSamples or github.com/FBSamples glTF renderer that shows how to do this with a very minimal abstraction renderer that uses OpenGLES in Java. So there's no abstraction here. You can see exactly how this works if you want to have a good introduction to how 3D rendering works on Android. So to put this together, I just kind of put it inside an AR core sample where basically it allows me to render my glTF scene, which is very trivial. It's just a single triangle on some surface. So the AR core gives you the SLAM surface, and now I can just render my triangle with glTF, with my glTF renderer. So let's talk about how we actually implement the rendering of this. So first, we want to parse the glTF. So that's pretty obvious. We're going to walk through the glTF, or the glTF JSON, and then we're going to parse the scene graph, and then we're going to figure out how to find the buffer data. So remember, this was our structure where we had our scenes, our nodes, our meshes, our buffers, our buffer views, and our accessors. So those are like the top-level array entities. And when we're going to parse this, all we do is we basically just parse out these top-level JSON arrays, and then we're going to inflate it and then keep it in like an array list or a vector or whatever. And the point being that now when we need to reference something within those arrays, we'll just do a quick index lookup. So this is how we do it, just using the JSON object API. So when we go to parse the actual nodes, we're going to try to find the information that we need to render. So we're going to go and we're going to get the mesh data. So now we fetch the mesh for each node. And then similarly, when we want to parse the mesh data, we're going to fetch the primitives and the attributes and so on and so forth in the indices. So basically just pretty straightforward parsing of the JSON to get at the actual data that we need. Now, the interesting part is when we actually parse the buffers. So it's super important that we aren't redundant or we aren't memory wasteful when we parse the buffers. So what we're going to do is we're going to parse that single buffer that we have only once. And even though we have a buffer view that looks at it 2 different ways, we're just going to use that same underlying buffer. So in this case, we have a data URI, so we just have to decode that data URI and then store it in a byte array, essentially. And then we're going to provide a byte buffer that is going to contain that array data. Now, when we use our buffer views, we're just going to look at a specific offset to find the data that we need. Now, of course, this is pretty simple for the data that we have right now because it's just a triangle. But when you have a very complex 3D mesh, this can be super big savings in terms of efficiency and memory. The next thing we're going to do is we're going to create a rendering representation from the data that we just got back from the JSON. So we need to convert it into data that can be rendered with the OpenGLES API. One thing to note is that we're going to be doing a draw call, a graphics API draw call per mesh primitive. So when we looked at this mesh data here. So you'll notice that there's a primitive section. You can also have multiple primitives. The reason why you'd want to do this is you might want to break down a very, very complex mesh into multiple sections so that it makes it more efficient to draw. So for each mesh primitive, we're going to do one OpenGLES draw call. So let's get back to here. And then, of course, we're going to extract the vertex and index data from the accessor. So now we're here, and we have the mesh data that we extracted, and then we have the primitive data that we extracted. And again, we're just following the indirection the same way that we jumped through the JSON. And then we're going to actually get to the raw data. So this is all that's going on here. It's pretty straightforward, but the source code is online, of course, if you want to, if you missed something. So the important part here is now finally getting to the vertex and the index data, which is what actually tells us how to render the scene. So what we're going to do is we're going to take that original byte buffer or byte buffer view that we looked at originally, and we're going to look at it two different ways depending on if it's the vertex buffer or the index buffer. And this is provided by the Java buffer API. So all we have to do is we look at it as a float buffer because we know that we're interpreting float data for the case of the vertex positions. And then we are going to apply the byte length and the byte offset and then just position the pointer inside that buffer object to the right position. Similarly, when we want to do the index buffer, we're going to do the same thing. So, actually, sorry. This is the way that you actually upload the data to the GPU. So now that we have the vertex data in memory, so that's here in our float buffer abstraction, then we need to upload it to the GPU. So this is the API that we use with OpenGLES to upload the data to GPU memory, so from system memory to GPU memory. So the key thing here is first we have to generate the buffers. That's what we do with GLGen buffers. And then we're going to do a bind buffers to, OpenGLES is state-based. So we need to bind a single buffer. And then we're going to say that we're going to upload the data. So that's what the GL buffer data call does. So now that we've uploaded that vertex data, just pointing to that float buffer, then we can get ready to draw. So drawing with OpenGLES, this is going to happen every frame because generally you're going to have animation and stuff that changes every frame. You can do optimizations for, like, if nothing changes in the frame, just don't re-render the scene because the screen is not going to change. So for each render object, we're going to attach the shaders. And if you're not familiar with shaders, shaders are programs that run on the GPU. There's the two most common ones are the vertex shader, which tells you what the final screen position of a vertex is. And a vertex is just a point in 3D space. So we need to do a perspective projection or an orthographic projection that maps from 3D to the 2D screen space. So that's what the vertex shader does. The other shader is the fragment shader, which gives you the final color for the pixel that's going to be on the mesh. So for each pixel on your geometry, you need to figure out what the color of it is going to be, and that's what the fragment shader does. So once you've attached your shaders, then you're going to bind the actual buffers. So we talked about the index buffer and the vertex buffer. And uniforms are just any state that you need to provide to the GPU to render in the shaders. And then finally, the call to GL draw elements is actually what executes and tells the GPU to go on and rasterize some triangles to create the mesh. So this is what it looks like. So for each frame, we're going to take our glTF render objects that we created. So we have this list of them. And again, these map to each mesh primitive in the JSON. And then we're going to bind the index buffer and the vertex buffer pointer. And then we're going to issue this call to GL draw elements with the index count, which is basically just how many elements we're drawing. And in this case, it's just 3 because we have the 3 vertices or the 3 elements that make up the triangle in our scene. And once we do that, then we have our glTF hello world scene rendered. Pretty straightforward when you're just looking at a triangle, but of course, this gets a lot more complex when you have a very complex mesh, but this is at the core exactly how everything is working. So if you understand this, you understand the fundamentals of 3D graphics rendering. And of course, we're just using like red as the default color, but you can also have materials. So we could have applied a texture to give the triangle some kind of image as a look, and we could have also provided some kind of lighting to change the way that the triangle looks based on where the light source is. Again, my sample glTF render code, so if you want to look more in detail, please check this out. And now let's talk about improvements in 3D posts. So we talked about glTF being the JPEG of 3D, but an important thing for being JPEG, or being like JPEG, is to have an encode and decode step, where you encode prior to transmission over the wire, and then you decode quickly on the client. So we need to look into a way to do that with 3D objects. So the first thing is to compress the meshes. So Google actually provided the glTF extension for mesh compression, or one of the standard ones, or the ones that's been ratified by Khronos, using their Draco mesh compression system. So this is an example, or these are samples of glTF models that are on the Khronos repository, where Google has achieved very good compression ratios with their Draco system. In some cases, they can get a 10-to-1 compression ratio. And this is super important because it turns out that the network transfer is generally the bottleneck in loading 3D scenes. So you can imagine when we're in Facebook newsfeed, we need to load each post very quickly because people are quickly scrolling through the feed. So we can't have a 40 megabyte glTF file. But if you can use mesh compression, then maybe you can load 4 megabyte glTF file over the wire and then just do a quick decode in time for loading. So mesh compression is super important. And it's generally pretty fast to do the decode. And again, this is just applied to the mesh data itself, so the actual vertex and index data. Now, another thing that's super important is texture compression. So the textures themselves, a lot of times when you want to have a mesh be less complex, what you'll do is you'll simplify the mesh, but then you'll still apply high resolution textures so that it still looks decent. So it's super important to also compress the textures. So one thing with texture compression is most GPUs support different texture compression formats. So because of that, you can't just use the same texture, a compressed texture across PC and mobile. So there's going to be different formats depending on which one. So this becomes a problem for glTF, which tries to be platform agnostic. So we need to find a solution for this so that we can do this without having to be specific to each platform. So this is actually Khronos' approach to it. So what they're doing is they're proposing this universal texture format, and the way that it's going to compression format, and the way that it's going to work is that it's going to be a format that you transcode on the client to one of the native formats. So the format would look the same from the higher level, but when you get it onto the client, it will try to transcode it to one of the platform-specific GPU texture compression formats. And the reason why we want to do this is we don't want to have to go through the whole JPEG decode step, essentially, and then pull it into binary or into bitmap data, because the bitmap is much, much bigger in memory than the actual texture data, or the actual over-the-wire transmission format data. So if we can just take the compressed texture and load it directly on the GPU, we can skip that decode step and we can save memory. So this is very important for complex scenes, and this is kind of the approach that Khronos is going so that they can have something platform agnostic. Now, of course, at Facebook, we can be a lot more practical about this, and what we'll just do is that if you're on Android, we know that we can serve you a certain compressed texture format. So we'll just serve you ETC2 or ASTC or one of the formats that works on our platform. And then if you're on web, we can serve you in DXT1 or one of the DirectX formats. So the next thing that is important in improving in 3D posts is to get better use of all the glTF 2.0 features. So far, we haven't implemented everything like blend shapes and animation, skinning, physically based materials. This is kind of a sample that Khronos put out of what you can do with glTF. So you'll see here that it has environment-based lighting. What that means is that the actual animated object here, which is that dog, it actually takes in the lighting from the scene. Now this is very, very important in AR. So if you want something to look realistic in the scene in AR, it needs to take on the lighting from the environment. Otherwise, it's going to stand out. It's kind of like, the early version of Pokemon Go, where it just had like this, Pokemon that's just rendered on top of the video feed, and it didn't look like it's actually part of the scene. So to make it feel like it's part of the scene, you need to render it, and it needs to take in all the lighting cues and the color reflections and the little things that you don't really think about, but it actually plays a big part in making something feel like it's part of the scene. So that's when we get into physically based rendering. So physically based rendering is a way to more accurately represent materials and how they interact with light when compared to traditional real-time models. This is an example of a glTF file loaded on the website Sketchfab. And you'll see that it's a very realistic rendering, which has the lighting from the environment. You see reflections, you can see roughness, and you can see properties that make it feel like it's very realistic. This is what most high-end game engines are doing these days to try to make a realistic, photorealistic render. So the way that this is done, you have your base mesh, like you can see there, and then there's different textures that are providing different material properties. So these are physical properties like roughness, how how metallic it is, how emissive it is, if it's emitting light, and then we combine these all together using light calculation formulas to provide the actual final output render. So you can see here. These are all like the different components from that glTF physically based rendering material. There's multiple textures that provide that. And then in the end, you get your final render, which looks super realistic and takes in the environment lighting. So if you're interested in physically based rendering, which is a huge topic on its own, Romain Guy worked on a physically based rendering library called Filament, which is used within the Sceneform API library that works with AR Core. And there's extensive documentation on the Filament GitHub page. They pretty much wrote a novel about physically based rendering because it's fairly complex, and the optimizations that we need to do to make it work performantly on Android are super important. So if you're interested in this is a really, really great resource. And the Filament library itself is a really good implementation of physically based rendering for Android. So that's pretty much my talk. That covers kind of, what glTF is, what we're doing next, and kind of how we're using it at Facebook. And what we hope that you get from this is that we know that the skill sets that Android developers are going to need in the future is going to be they're going to have a better understanding of 3D rendering and things that you're going to need when you start doing Android apps that go into AR and VR applications. But there's also different applications that even for our 2D Facebook application, we find use cases where 3D makes sense, and things like 3D photos and just being able to render artists' art directly on Facebook. So you might find that right now it might not match your use case, but you'll see that kind of in the future there's going to be a ton of use cases where you're going to need this skill set. So I'm hoping that this introduction to 3D scene rendering and describing what we're doing at Facebook helps you guys in the future. So, do you have any questions? Yeah, so is there a standard animation format? So the glTF spec itself describes how animation data is kept within the file format itself. So you can have node animation, so like I showed you with the car, where you're applying on each node a matrix to basically do the transformation or the rotation scale translate. So that's one kind of animation, so that will allow you to rotate your layer or rotate your node and rotate your children nodes. But there's also more complex animation. So there's joint-based animation. So that's when you describe the joints. So if I'm rendering a person, I would describe where their joints are, and then you would be basically giving information that tells you how to move the joints and how to animate them separately, and then that joint-based movement will be applied to every node that is within that joint, if you get what I'm saying. So that's joint-based animation or skinning, and then you apply textures that apply to the arm so that you can make it look like a proper arm. There's also blend shapes. So blend shapes is like when you're doing facial animations or something more squishy, where there's a lot of deformations. So glTF also supports blend shapes and a way to describe that. So all that stuff is still going to be kept in the GLB. So it's going to be kept in the binary part. And generally you would have like keyframes for the animation and it would be appended. And the JSON itself would tell you where to get that data. So it'd be similar to the accessor that tells you where to get the data from the buffer. The same thing would be applied with the animation data.
So is it ever possible for you have to transport it potentially?
Yeah, so he's asking, if it's possible for GPU vendors to support the common format for texture compression. Yes, absolutely. But the problem is, what do you do for all the existing phones and hardware out there? Because the compression format is not just a software level thing. It's something that needs hardware support.
So I was just wondering if there's any movement for GPU vendors to.
Oh yeah, absolutely. Yeah, so definitely, we're trying to solve it in the practical way right now for existing devices, but in the future, yes, there's definitely GPU vendors trying to get together and solve the problem of what is the ultimate texture format that we can use in all use cases. So that is a collaboration that has to happen between all the vendors, but the problem also ends up being that GPUs are different and each have proprietary implementations that work better in certain cases. So it's kind of hard to make something that is optimal for all cases. But if we have something that's standard in the industry and everyone else has to support it, then I think that's the way that this is going to happen. But again, that will only help us 5 years down the line when everyone is on those platforms. And even if you're on Android, probably not everyone's going to be on those platforms. Cool. So I think we're over time. So thank you, everyone.